Week 8 to 9, Introduction to Bagging and Random Forests. Welcome! Today we will learn about ensemble methods, bagging and random forests. These methods help improve prediction accuracy by combining multiple models. We will use real diabetes data and apply bagging and random forests to predict diabetes risk. Let us begin our data mining journey. Running the cell now. Think, have you ever heard of the term ensemble used in other areas? Let us turn off warnings before we start. We turn off warnings. This keeps our notebook tidy and easier to read. Import NumPy as NP. We set the random seed to 42 for reproducibility. Running the cell now. This code sets a fixed random seed and suppresses warnings, ensuring our results are reproducible and the output stays clean while we explore bagging and random forests. Notice there's no direct output here. This setup step is crucial for consistent model training and clear, focused learning ahead. Try running the cell. Notice how messages from libraries disappear. Let us get our data ready. We prepare to load the Pima Indians diabetes dataset, which contains medical data. We import the pandas library for data manipulation. We specify the URL where the dataset is hosted online. We define the column names to label each data field clearly. We read the dataset from the URL into a pandas data frame with the given column names. We print the shape of the data frame to see the number of rows and columns. We print the first 3 rows to preview the data. Running the cell now. Here, we loaded the Pima Indians diabetes dataset, which has 768 rows and 9 columns including features like glucose and BMI, plus the target outcome indicating diabetes presence. Notice the first 3 rows show a mix of values and outcomes, giving us a sense of the data structure we'll use to train our bagging and random forest models to predict diabetes risk. This step ensures we understand the dataset shape and key variables before applying ensemble methods. Take a look. What information do you see in these first rows? Let us check if our data has missing values. We want to know if the data has any gaps or missing spots. This helps us know if we need to clean the data later. Running the cell now. Here, we checked for missing values in our diabetes dataset and found none across all columns. This is important because ensemble methods like bagging and random forests require complete data to build reliable models without additional imputation steps. Ensuring clean data at this stage sets a strong foundation for accurate predictions later. Look for any numbers greater than 0. That means some values are missing. Sometimes, zeros can mean missing in medical datasets. Let us check. We start by noting that zeros in some features might actually represent missing data. We define which columns may have these 0 placeholders. We go through each of these columns one by one. For each column, we count and print how many 0 values it contains. Running the cell now. This output shows the count of 0 values in key health measurement columns, which likely represent missing data rather than true zeros. Notice how some columns, like insulin and skin thickness, have a large number of zeros, indicating potential data quality issues to address before modeling. Identifying these helps ensure our bagging and random forest models are trained on clean, meaningful input for better predictions. What would a BMI or glucose of 0 mean in real life? Now let us replace strange zeros with missing values in our data. We start by noting that zeros in some columns might actually be missing values, so we will replace them. We import the NumPy library to use its nan, not a number, value for missing data representation. We loop over each column that has zeros which we consider suspicious and might mean missing data. Within each column, we replace all 0 values with np.nan to mark them as missing. Finally, we check how many missing values are now present in these columns after replacement. Running the cell now. This output shows the count of missing values after replacing zeros with nan in key health columns, highlighting potential data quality issues. Notice how insulin and skin thickness have especially high missing counts, which is important because accurate imputation or handling of these gaps will impact model performance in our bagging and random forest predictions. This step ensures we're aware of data imperfections before building robust ensemble models. How many missing values do you see now? We are getting our data ready for mining. Now we fill in the missing values with the median of each column. Filling with the median keeps our numbers realistic and avoids outliers. This common method helps us avoid biasing our results. Running the cell now. Here, we fill missing values in the dataset by replacing them with the median of each column. This step ensures our models, like bagging and random forests, receive complete data without bias from missing entries. Notice how this pre-processing maintains the shape and integrity of the data, setting a solid foundation for more accurate predictions. Practice: why do you think we use the median instead of the mean here? Time to explore the summary statistics of our clean data. This gives us a snapshot of the minimum, maximum, median, and other statistics for each column. It is a great way to spot unusual data, see the spread, and understand the range of our features. Running the cell now. This summary reveals key statistics for each feature in the diabetes dataset, such as mean, range, and distribution spread. Notice the varied scales. For example, glucose ranges from 44 to 199, while BMI varies between 18.2 and 67.1, highlighting the importance of considering feature scales before modeling. Understanding these distributions helps us prepare and tune bagging and random forest models effectively for robust diabetes risk prediction. Check: which feature has the largest range? Which feature has a very small spread? Let us plot our data to see how each feature is distributed. This comment explains that we are going to plot histograms for each feature in the dataset. We import the matplotlib plotting library to create visualizations. We plot histograms of the data frame's features to observe their distributions, then adjust layout and display the plot. Running the cell now. This output shows histograms for each feature in the diabetes dataset, giving us a clear view of their individual distributions. Notice the range, skewness, and spread of key columns like glucose and age, which can influence model performance. Understanding these patterns helps us appreciate why bagging and random forests, which reduce variance, are effective for predicting diabetes risk. Try to spot any strange shapes or long tails. Which variables are most unique? Bagging, bootstrap aggregating explained. Bagging builds many models from random pieces of the data. Votes from these models are combined for the final answer. This can stabilize and boost performance, especially for unstable models. We will try bagging with decision trees next. Running the cell now. Can you imagine other places where averaging many results might help? Time to split the data for testing how well our models perform. We start by adding a comment to explain that the next step is splitting the data into training and testing sets. We import the train_test_split function from Sklearn to help us split the data. We create the feature set X by dropping the outcome column from the data frame. We create the target variable Y by selecting the outcome column from the data frame. We split X and Y into training and testing sets, using 30% of the data for testing and setting a random state for reproducibility. We print the shapes of the training and testing feature sets to see their dimensions. Running the cell now. Here we confirm the data split into training and testing sets, with 537 samples used for training and 231 for testing, each containing 8 features. This setup is essential for bagging, as it ensures models train on a subset while being validated on unseen data, allowing us to assess how well bagging stabilizes predictions across different samples. Why do you think we need both a trained set and a test set? Let us build our first bagging classifier using decision trees. This comment explains we're using bagging with decision trees. We import the bagging classifier from Sklearn.ensemble. We import the decision tree classifier from Sklearn.tree. We create a bagging classifier with 50 decision trees and a fixed random state. We train the bagging model using the training data. We compute the accuracy of the bagging model on the test data. We print the test accuracy of the bagging classifier. Running the cell now. The output shows a test accuracy of 0.740, indicating the bagging classifier's performance on unseen data. This reflects how combining 50 decision trees, each trained on random subsets, helps stabilize and improve prediction accuracy compared to a single unstable tree. Notice how bagging reduces variance by aggregating diverse models to boost overall reliability. Was the accuracy better or worse than you expected? Let us compare bagging to just a single tree. We start by indicating we'll compare a single decision tree model. We create a decision tree classifier with a fixed random state for reproducibility. We train the decision tree on the training dataset. We evaluate the trained tree's accuracy on the test dataset. We print out the test accuracy of the single decision tree model. Running the cell now. This output shows the accuracy of a single decision tree on the test data, which is about 69.7%. Notice this baseline performance before bagging. It highlights the instability and limited accuracy of one model trained on the full dataset. The intent here is to establish a reference point to later compare how aggregating many trees can improve and stabilize predictions. Notice which accuracy is higher. Ensembles usually help most on tricky data. Random forests, smart bagging. Random forests are a form of bagging, but smarter. They add randomness by letting each tree look at only some features at each split. This helps make the trees more different from each other. It is a very popular and powerful method for both classification and regression. Running the cell now. Let us train a full random forest classifier. This comment introduces the use of the random forest classifier model. We import the random forest classifier class from the Sclern library to create the model. Here we create the random forest model with 100 trees and set a random seed for reproducibility. We train the random forest model on our training dataset with features x_train and labels y_train. We evaluate the model's accuracy on the test data using the score method. Finally, we print out the test accuracy in a readable format. Running the cell now. The output shows a test accuracy of 0.749 for the random forest model, indicating it correctly predicts about 75% of the test samples. This reflects how the smart bagging approach improves performance by combining multiple diverse trees, each trained on different feature subsets, to create a strong overall predictor. Notice that this accuracy result confirms the benefit of adding randomness to reduce overfitting compared to a single decision tree. Ask yourself, did random forests outperform regular bagging? Now we will see which features were most important to our model. This comment introduces the topic of feature importance in the model. We retrieve the importance scores of each feature from the random forest model. We loop through each feature and its importance score to display them. We print each feature's name along with its importance, formatted to 3 decimals. Running the cell now. This output shows the feature importances calculated by the random forest, highlighting which variables most influence the model's decisions. Notice how glucose has the highest importance, meaning it was the most useful feature across the trees, while others like skin thickness contributed less. This aligns with the lesson's focus on how random forests smartly use subsets of features, allowing key predictors to stand out in their influence. Which feature surprised you by being important or unimportant? Let us visualize where our model gets things right and wrong. This section introduces the visual confusion matrix for the random forest model. We import functions needed to compute and display the confusion matrix. We predict the labels for the test dataset using the trained random forest model. We compute the confusion matrix by comparing actual and predicted labels. We create a visual display object for the confusion matrix. We plot and show the confusion matrix visualization. Running the cell now. The confusion matrix shows how well the random forest model classified each class in the test set, with the diagonal cells representing correct predictions. Notice the spread of values off the diagonal indicates where the model made errors, helping us evaluate its accuracy and robustness. This visualization connects to the lesson by highlighting how the randomness in feature selection leads to a diverse, yet accurate ensemble. Can you see which kind of mistake the model makes more often? Let us try entering our own data for a prediction. Introduce the interactive diabetes prediction process. Create an empty list to store user inputs for each feature. Start looping over all feature names in the dataset. Prompt the user to enter a value for the current feature. Convert the entered value to a float and add it to the list. Use the trained random forest model to predict diabetes from the input data. Convert the numeric prediction into a readable label, diabetes or no diabetes. Display the prediction result to the user. Running the cell now. This output shows a prediction made by the random forest model on a custom input, returning no diabetes for the values entered. Notice how the model applies its learn patterns to new, user-provided data to make a real-time classification. This illustrates how random forests can generalize from training data to smartly predict unseen cases by aggregating decisions from many diverse trees. Try entering values from a real or imaginary case. Compare the prediction to what you expect. If you enjoyed this interactive part, please like and subscribe so you do not miss future hands-on data mining lessons on YouTube. Mini project, bagging versus random forests. Let us see if bagging and random forests predict well for a new set of cases. You can try different numbers of trees or change the feature set to see what happens. Could you beat our best score with a new strategy? What might you change next? Write your ideas below or try with the code. Running the cell now. Experiment, try using 25 or 200 trees instead of 50 or 100. Record the accuracy each time. Let us check how the number of trees changes our bagging accuracy. This example explores how changing the number of trees in bagging affects performance. We loop over 3 different values for the number of trees, 10, 50, and 200. For each value, we create a bagging classifier using that many decision trees and set a fixed random seed. We train the bagging model on the training data. Next, we evaluate the trained model on the test data to get its accuracy score. Finally, we print the number of trees used and the corresponding test accuracy with 3 decimal places. Running the cell now. Here we see how changing the number of trees in the bagging ensemble affects test accuracy. Notice that increasing trees from 10 to 50 doesn't improve the score, and 200 trees slightly raise it but don't guarantee better performance. This highlights the point that simply adding more trees doesn't always lead to better results. Tuning the model carefully is key. Try to think, is there a point where adding trees stops making a big difference? Saving your trained model lets you use it later without retraining. This is an extra tip about saving and reloading your random forest model. We import the joblib library, which helps us save and load Python objects like models. Here, we save the trained random forest model to a file named rf_model.joblib. Now, we load the model back from the saved file into a new variable rf_new. Finally, we print the score of the reloaded model on the test data to confirm it works correctly. Running the cell now. Here we see the test accuracy of the reloaded random forest model, confirming it performs consistently with a score of 0.749. This step shows how to save and reuse your trained model, which is crucial for deploying or further testing without retraining. Notice that the accuracy remains stable, verifying the model's persistence and reliability after saving. Have you ever saved your progress in a game or project? This is similar for models. Troubleshooting and best practices. When to use bagging or random forests. When single models overfit your data. When accuracy is unstable across runs. Always check the importance of your features. Use random_state for reproducibility. Try tuning the number of trees or tree depth. If accuracy is low, check for data quality or biased splits. Ask for help on forums or from teachers if you are stuck. Running the cell now. Feel free to test another classifier to compare with bagging and forests. This is a practice suggestion to try a different classifier. We import the kneighbors classifier from the Sklearn library. Create an instance of the kneighbors classifier. Train the KNN model using the training data x_train and y_train. Evaluate the accuracy of the trained KNN model on the test data. Print the test accuracy of the KNN classifier formatted to 3 decimals. Running the cell now. The KNN classifier here achieves a test accuracy of 0.675, which is moderate but may still suffer from variance or overfitting depending on the data. This output highlights why, in cases where single models like KNN show unstable or suboptimal accuracy, applying bagging or random forests can help improve stability and performance by combining multiple models. Challenge: try 5 neighbors instead of the default. What changes? Recap: what we learned. Bagging helps average out errors with many trees. Random forests add feature randomness, making trees more diverse. These methods are reliable for tricky or noisy data. Checking feature importance can give you insights for real decisions. Always compare ensemble methods with single models. Congratulations! You are building skills found in industry data science jobs. Running the cell now. Thank you and next steps. If you learned something new, hit thumbs up and subscribe to the channel. Try the challenge exercises for extra practice. Ask questions in the comments and share your own results. Happy mining! Running the cell now.